What is hypersonics? Hypersonics is the study of objects traveling faster than Mach 5 or 5 times the speed of sound. Being able to conduct research at this speed allows for the study of how materials and vehicles react to extreme heat, low pressure, and high friction. On Earth, this speed would be about 1700 meters per second. However, our vehicle only needs to reach speeds of 1200 meters per second to become hypersonic on Mars due to its low atmospheric density. This creates a unique challenge of generating lift, which is needed for sustained flight and scientific studies.
Mars presents a considerable challenge for generating lift because of its extremely sparse atmosphere. Traveling at hypersonic velocities, however, does ease this design requirement. Traditional hypersonic aircraft on Earth often use large delta wings. This design choice is largely driven by heat buildup at hypersonic velocities, requiring large sweep angles. The SR-71 and the Space Shuttle are examples of this design, which also provides greater control for aircraft operating at high speeds. Initially, delta wings seem like the clear choice, but they may not be the best for all mission types. The challenge of heating is substantially less significant on Mars thanks to the low pressure. Instead, a more significant requirement for the wings of a Martian aircraft may be to produce as much lift as possible, or to achieve the maximum lift-to-weight ratio. Wings that achieve this goal often have a high aspect ratio, like the Lockheed U-2 or high-altitude gliders. A set of straight or swept wings may be needed to achieve the high performance characteristics required of this vehicle. Another advantage is a greater range of altitudes, enabling more varied scientific observations and increased range and endurance. The choice of wing type is then highly dependent on the mission profile. A vehicle designed to spend significant time at high speeds would benefit from the control and thermal properties of a larger delta wing, while a high-altitude vehicle may instead opt for more efficient wings, providing for significantly more data to be collected and for greater control during landing. Given the requirements of this vehicle, likely spending longer periods at high speed, delta wings may be more desirable and may give better performance characteristics.
Hypersonic flight on Mars could present a new avenue for Mars atmospheric research. Because of the limitations of the current Martian rovers, the bulk of atmospheric research has taken place at the surface. The little we do know about the conditions at higher altitudes has come from the entry and descent of the mission's landings. Hypersonic flight would allow us to conduct research at constant altitudes, giving us more accurate data for Mars's atmosphere. Data collection could additionally be repeated at various locations, altitudes, and velocities for increased precision and accuracy of results. To obtain readings for atmospheric data, the spacecraft would need to be equipped with multiple instruments capable of capturing the needed data, something similar to Perseverance's Mars Environmental Dynamics Analyzer, or MEDA for short. MEDA makes weather measurements including wind speed, temperature, humidity, and also measures the amount and size of dust particles in the Martian atmosphere. Similar to MEDA, the instrument required would measure temperature, pressure, density, and altitude.
To maximize maneuverability, our design incorporates large control surfaces managed by a hydraulic motor control system. We chose a hydraulic system because it would be more suitable than an electric one. While an electric motor control system would be lighter, it would have complex wiring and a higher probability of failure. The hydraulic system, however, can handle higher hinge loads and is much more reliable. It is important to remember that with higher speeds and reduced air density, control surfaces become less and less effective. So when thinking about the size of the control surfaces, we felt it more appropriate to prioritize the efficiency and ease of the takeoff and landing of the vehicle rather than flight control. In doing so, the control surfaces would be on the larger side than normal. While this would increase the weight of the hydraulic system to operate and handle the higher hinge loads, this comes with the benefit of more control when trying to vertically land the vehicle on the Martian surface. Our vehicle utilizes a low-thrust hydrazine engine to maximize the small amount of thrust required for takeoff on Mars. This also allows for our engine to be smaller and lighter than a standard jet engine. There are many options for propellant combinations with different benefits, but using hydrazine and liquid oxygen would provide the best results. While we have already sent numerous hydrazine engines to Mars, like those used on the Sky Crane landing systems for the rover missions, these engines only run on hydrazine. Adding liquid oxygen or nitrous oxide as an oxidizer would increase performance, enabling longer missions.
To conclude this presentation, we would like to summarize the design decisions we've made while showing off what a potential design might look like. In this model, we've assumed that the mission would require the use of delta wings. Some details not previously discussed in our model are the instrument bay, RCS system, and landing legs. The instrument bay is placed on the underside of the fuselage, enabling research of the Martian surface. A reaction control system towards the nose aids in landing and takeoff, and rear-mounted landing legs keep the aircraft stable when not in flight. Thank you for watching our presentation on hypersonic flight.